Okay, through the example that we worked on today, I want to convince you that everything you need to know about simple harmonic motion is right here, and then you just have to have a few concepts like energy conservation and so forth. Doesn't mean that you have those concepts, but maybe this will motivate you to revisit those concepts and expand your ability to apply them. Okay, so in the first place, the premise of any simple harmonic motion is that your net force is equal to negative kx, where x is some position measurement. Okay, net force is negative kx. This is true if and only if mx double prime equals negative kx. Now that's really simple because the primes implicitly indicate derivatives with respect to time, and x double prime is the second derivative of your position function x, making this the acceleration, so you have net force equals mass times acceleration. No surprise there. Now, you don't know yet the theory of differential equations, but you can simply, and did last time, easily verify that if x equals b cosine of omega t plus c sine of omega t, where b and t are constants, and omega is equal to the square root of k over m, which I probably should have written down here, but we saw it last time and you know what it is. At least you're supposed to know what it is. Okay, and of course, over a 2-day span, maybe you didn't really lock this in, but hopefully you have it in your notes in such a way that you find it easily. Okay, well, b and c are arbitrary constants. Omega is also a constant, but it's equal to the square root of k over m. Okay, well, and of course m is the mass that's oscillating in simple harmonic motion. Right there is a position function, position as a function of time. Now that position function is equivalent to this position function or this position function, where a depends on the values of b and c, and phi depends on the values of b and c in a way that's just simple high school trigonometry. The cosine or the sine of a sum of two angles is what? Okay, one part of the sum will be a cosine and a sine. The other, well, I'm not going to, you can apply those. Okay, we might well digress to get that. But by that simple connection, this is equivalent to this. Okay, the values of a and phi would determine the values of b and c, or if you had the values of b and c, they would determine the values of a and phi. Also, independently, if you plug this into the equation, you get an identity. Okay. In other words, you can verify the equation for this function, or for this function. Each function has two arbitrary parameters, b and c here, a and phi here, a and phi here. Now the phi you get here and the phi you get here won't be the same. You have different values of phi, and from here to here or from here to here, the value of phi differs just by 90 degrees or pi over 2 radians, or negative 90 degrees pi over 2 radians, depending on what direction you go in, because the sine and cosine functions are out of phase by 90 degrees or pi over 2 radians. Okay, so there's not a whole lot of mathematical content here. It's just all high school mathematics and a few little easy first semester calculus, the derivatives of sine, cosine, and the chain rule, and you can get all this. That's all you need to do simple harmonic motion. If you understand energy conservation, it's really pretty much all you need. So we'll proceed and see why. Now, we spent the whole class trying to solve a tangible situation with a mass hanging from a rubber band and oscillating. And we abstracted that to the ideal case where no energy is lost, and then we used this to analyze the situation.